Hello students, today I am discussing on image sampling and quantization. So we all know what is an image. An image is a function, two-dimensional function of f of x comma y, where x and y are spatial coordinates and f, the amplitude f at any pair of coordinates represents the intensity level or gray level of an image at that particular point. So f is the amplitude, or it is also the intensity level at that particular point. So now these images are classified into two types. We know that images are classified into two types. They are analog image and digital image. Right. So what do you mean by analog image? So if the values of x, y and f are all continuous, we say such an image an analog image. So what do you mean by digital image? If the values of x, y and f are all finite and discrete quantities, we say such an image a digital image. Okay. For example, so if this is an image, so here xy represents the coordinate values. X is equal to 0, y is equal to 0. X represents the number of rows and y represents the number of columns, right? So here first row, first column. So first row, second column. So first row, third column, right? So like this. And this pixel value is, like the location of this pixel is second row and first column, second row, second column, like this. This is how we represent an image. So what is the meaning of f of x comma y here? X and y represents the spatial coordinates, that is the spatial locations of each and every pixel, where the f represents the amplitude of each and every pixel, that is the intensity value of each and every pixel. Okay. So now you know what is a digital image, but why we have to convert an analog image into digital image? Sometimes you have some images, a low quality images with full of noises, and to extract the information from that image you have to remove the noise from that image, right? And sometimes in some of the images you have to extract the required information. So to do all that, and sometimes for some images you have to resize that particular image, and in order to store that image you have to modify that image. So in order to do all that, that is to process an image, it should be converted into digital form. So digital images are very easy to process. Okay. So some of the advantages of digital images are fast processing, cost effective and effective storage and efficient transmission, and it is easy for human interpretation. So we go for processing of digital images than analog images. So we need to convert analog images into digital image. So how to convert an analog image into digital image? For that we have two intermediate steps. So to convert an analog image into digital image, there are two intermediate processes. They are sampling and quantization, and it results with digital image. convert an analog image into digital image, so we have to go for two intermediate processes. They are sampling and quantization. Then it results with a digital image. So what do you mean by sampling and quantization? Sampling means digitizing the coordinate values x and y is called sampling. So here in analog images, x, y and f are all continuous, right? So their values are continuous. So digitizing x and y, both the coordinate values, is called sampling, and digitizing the amplitude value is called quantization. So digitizing coordinates x and y is called sampling, and digitizing the amplitude value, that is the f, is nothing but quantization. So now let us understand the concepts of sampling and quantization better with an example, with an illustration. So under this, so to understand the concepts of sampling and quantization, let me illustrate with an example. For that, let me consider a continuous image f of s comma t. Okay, let this be a continuous image. So this is a continuous image. So let me consider a scan line from A to B in this continuous image in order to understand the concepts of sampling and quantization. Okay. So this it is very difficult to show the intensity levels and intensity variations of this object on this blackboard. So look at this image, the same image. Here you can notice that the intensity levels within the object is being varied, right? So this is the continuous image which I have considered. So I have to convert this continuous image into digital image. For that, I have to perform two intermediate steps. First is sampling and next is quantization. So in order to sample this this image, first I will convert this image into one-dimensional function. So I am converting this continuous image into one-dimensional function. That means this is a plot of amplitude along the line segment AB. So this gives the amplitude or the intensity levels along the line segment AB in this continuous image. And this random variations are due to the presence of image noise. Okay, and here you can observe that here till this point here the intensity is constant, and even here the intensity is constant, that is represented here, and at the middle the intensity is varied more. So that is how I have shown in this figure. Now in order to convert this into digital image, first I should sample this image. So how do you sample this image? Sample means digitization of the coordinate values x and y, right? So for that, let me consider equally spaced locations which is shown as vertical tick at the bottom part of this figure. Okay, and now the samples are considered in correspondence to these spatial locations. Here I have considered samples in correspondence with these spatial locations. Here the samples are shown as small white squares, okay, and here the samples have been given digitized values based on this vertical tick mark. So digitizing this samples based on the spatial location is nothing but sampling, right. So now these samples should also be digitized with respect to intensity levels. So for that, consider So now look at the intensity scale which is on the right side of this figure. Here there are 8 discrete intensity levels. Here each sample is assigned with the corresponding intensity values, which I call as quantization. Okay, so digitizing the samples based on the spatial location is nothing but sampling, and digitizing the samples based on the intensity levels is nothing but quantization. So this is how we perform sampling and quantization on the continuous image. Now next, the image, the resultant image. So the resultant image is the digitized samples with respect to spatial location as well with respect to intensity levels. So performing this operation starting from the top of the image line by line results with the digital image. Okay. So now look at this figure. So figure 1 is the continuous image which is projected on a 2-dimensional array, and figure 2 is the result of sampling and quantization. Here each and every sample is assigned with a discrete value based on spatial location as well the intensity level. So this is how sampling and quantization is done on a continuous image in order to obtain a digital image. Okay. Next is representation of digital images. So how do we represent these digital images? So to illustrate that, let me consider a continuous image f of s comma t where s and t are continuous variables. So in order to convert this continuous image into digital image, we have to perform 2 intermediate steps, that is sampling and quantization. So in order to sample this continuous signal, let us project this continuous signal on a 2D array having m number of rows and n number of columns, which forms a digital image. Okay, and that digital image I call as f of x comma y. You know what is digital image? Here x, y and f are all finite and discrete quantities. So now the coordinates x and y varies from x is correspondence with the rows, number of rows, y is correspondence with the number of columns. So x varies from 0, 1, 2 up to m minus 1 and y 0, 1, 2 up to n minus 1. Right. So when a continuous image is converted into digital image, I call that image as f of x comma y, where x and y represents number of rows and number of columns. Okay, and there are three different ways to represent these digital image. So look at this figure 1. Here in this image, here the image is represented as surface. So here this image has three axes. X and y represents the spatial coordinates, where the third axis is f of x comma y, which represents the intensity level. This f of x comma y is a function of the spatial coordinates x and y. So this is the first type of representation of digital image. Okay, and this type of representation is not preferable because when you deal with complex images which has very too many details, then interpretation of these images with this representation becomes very difficult. So usually we do not prefer this kind of representation. Okay, so the second type of representation of digital images is as shown in this figure. So here the images are displayed as the visual intensity levels. Okay, here the f of x comma y is a digital image which is represented as the visual intensity level. That means this is most familiar. Here f of x comma y values, that is the intensity values, are like as it would appear on the monitor of TV screens and as it appear on the photographs, right. So this particular image has three discrete intensity levels: white, black and gray level. Okay, so here the black is represented by 1 and white is represented, black is represented by 0 and white is represented by 1. The intermediate gray level is represented by 0.5. So this type of representations are usually used in printers, okay, as well in publishing and all. Okay, here this representation is most widely used. Okay, next is the third type of representation, that is numerical array. So look at this figure. This shows the third type of representation, that is the numerical array. So here in this, the f of x comma y, that is the intensity levels, the values of f of x comma y is represented as numerical values of that particular pixel. Okay, so here this is in the form of array where this contains the numerical values of f of x comma y. Okay, so this is how it looks, and this type of representation is most widely used in developing algorithms and in processing of digital images. This is the one representation which is used most widely. Okay, so among the three representations which I discussed now, which I showed till now, the second and third representations are most widely used, whereas the first type of representation is very rarely used. Okay, so now and this digital image f of x comma y can also be represented in the form of mathematical equations, that is in the form of array and matrix. So, f of x comma y can be represented in the form of matrix. So, here it is f of 0 comma 0, f of 0 comma 1, x represent number of rows, y represents number of columns. First row, first column, first row, second column, first row, third column, first row, last column. So, first row, second column, so last row, first column. So, this is last row, last column. So, this is how the digital images are represented in the form of matrices. So, this method is most widely used in developing algorithms and for processing of images. Okay? And here the m represents number of rows, n represents number of columns. There is no restriction with respect to the values of m and n, except that m and n should be positive integers. It should be positive integers. Except this, there is no other restriction. Whereas with the number of intensity levels, there are some restrictions that is due to the hardware considerations and storage capabilities. Okay? So, the number of intensity levels, where f represents the intensity level at that particular pixel, but I am talking about the number of intensity levels. So, the number of intensity levels are represented as L, and which is always equal to the integer power of 2. Okay? So, L is always equal to integer power of 2. Okay? Where k is the integer, positive integer. So, the number of intensity levels is always restricted to the integer power of 2. This is because of the hardware considerations as well as the storage capabilities restrictions. Okay? So, now also that there is a term called dynamic intensity range, which describes the minimum and maximum intensity range. Dynamic intensity range. Dynamic intensity range is a ratio of maximum intensity level to maximum measurable intensity level. Maximum measurable intensity level to minimum detectable intensity level. So, maximum measurable intensity level is also called as saturation, and minimum detectable intensity level is also called as noise. So dynamic intensity range describes the maximum and minimum limits of the intensity level, and it is the ratio of maximum measurable intensity level to the minimum detectable intensity level. So maximum measurable intensity level is also nothing but saturation. This means that the intensity level beyond this saturation level is clipped off, and the minimum detectable intensity level is nothing but noise. This means that the intensity level below this noise level is not a true intensity value. Okay. So this describes the maximum and minimum intensity level, which we call as dynamic intensity range. Also, for the digital images f of x comma y, the number of bits can be calculated. The number of bits required to store this particular image is represented by b, and which can be calculated by using the formula m cross n cross k. So here b represents the number of bits which is required to store that particular digital image, and m is number of rows, n is number of columns, k is the integer. Okay. So if the image is having same number of rows and columns, that means if the number of rows and columns are equal, then if m is equal to n, the number of bits required to store this image is called n square k. So now, if at all you know this n and k value, easily you can find the number of bits required to store that particular image. Okay, and this is the table which shows the number of bits required to store the images for varying values of n and k. Okay, and here the L represents the intensity level. So take a look at this table for varying values of n and k. So now we understood the concept of sampling and quantizing, that is how to convert an analog image into digital image, and then next we understood how to represent these digital images and how do we represent in the form of arrays, and what are the three different types of representations, and also we studied how to find out the number of bits required to store the image, all that. Right. So next is spatial and intensity resolution. So spatial resolution means it is the measure of smallest discernible detail of an image. So this is also called as the dots per unit distance, or it can also be called as pixels per unit distance, dots per unit distance, or pixels per unit distance, or it can also be called as line pair per unit distance. So spatial resolution means it is the measure of smallest discernible detail and in an image, and it is also called as dots per unit distance, pixels per unit distance, and line per unit distance, and it is used according to the application. In US they usually prefer dots per inch, that is DPI form, dots per inch format. So dots per inch means the number of pixels present in this unit distance, that is for one particular inch. Okay. So this type of representation is used widely in newspapers, that is in printing and publishing. So for a newspaper, a newspaper has a resolution of 75 dots per inch, and a magazine has a resolution of 133 dots per inch and a glossy brochure has a resolution of 175 dots per inch. So, as the number of dots per inch increases, the resolution of the image increases and hence the quality of the image also increases. Okay. So, this is what usually they use in US. And next is intensity resolution. As well, for spatial resolution, a good example is your digital cameras. A 20 megapixel camera gives very high resolution and hence the image quality, right, compared to 8 megapixel camera. So, that is how if the number of pixels per unit distance increases, the quality and resolution of the image increases. Next is intensity resolution. Intensity resolution is a measure of the smallest discernible change in intensity levels. Okay. So, that is, there are different intensity levels. The smallest discernible change in intensity level is nothing but intensity resolution. Okay. So, here for example, usually like this intensity level, as I told earlier, the intensity level, number of intensity levels is the integer power of 2. This is how we calculate, where k is an integer, right. Usually the number of intensity levels most widely used is 8-bit and 16-bit intensity levels, and 32-bit is very rarely used. This is very rarely used and this is most widely used. Okay. So, here if at all you observe, the spatial resolution depends on the number of samples, whereas the intensity resolution depends on the number of intensity levels. That means here this depends on the x and y value and the intensity resolution depends on f, the amplitude, number of intensity levels. Okay. So, the last one is image interpolation. Before going with image interpolation, I just wanna give some examples for spatial resolution and intensity resolution. As I told earlier, as the number of pixels per inch increases, the resolution also increases and the image quality also increases. So, to illustrate the effect of reduction of spatial resolution, let me consider an example. So, look at this image. So, now here the first figure is having the DPI value of 1250. Okay. So, this is a very high quality image. Now, look at the second image, okay, one next to that. So, this is having the DPI value of 300. Okay. So, now look at this image, there is some image degradation and you can notice that degradation in that long needle, right. Now, look at this third image. So, this is having a DPI value of 150. Okay. So, now here this is more degraded compared to 300 DPI image, right. So, here you can observe that the edge, the circular edge as well the small needles is being degraded, right. And next the last image is having DPI of 72. Now, here you can observe that many of the features have been degraded, right. So, the image quality is also very poor in this image. So, when there is a reduction with the spatial resolution, then the image quality also reduces. So to illustrate that, this is one good example. Okay. Next, to illustrate the intensity resolution, the reduction in intensity resolution, let me consider another example. So now look at this picture. So here there are 8 images, right? Here these images are of different intensity levels depending on the value of k. So here the first image is having the value of k varies from 8 to 1. Okay, we know that the number of intensity levels is equal to 2 power k, right? Here this first image is having the value of k is equal to 8, therefore L is equal to 2 power 8 is nothing but 256. So here the number of intensity levels in image 1, the first image, is 256 levels. Okay, hence the quality of the image is good. Now when look at the second image where k is equal to 7, therefore L is equal to 2 power 7, which is equal to 128. Now in second image the number of intensity levels decreased from 256 to 128. Now the quality is also decreased. So similarly, when k is equal to 1, L is equal to 2. So here you have only 2 discrete intensity levels, that is 0 and 1. Okay, 0 represents black, 1 represents white. So this is a binary image. So look at that last image. Last image is having the k value is equal to 1, therefore it has only 2 discrete intensity levels, black and white, which we call as a binary image. So when you compare this last image with the first image, we can see that the resolution is very poor. The intensity resolution is very poor of the last image when compared with the first image, right? So you can observe that as the value of k decreases, then the intensity resolution also decreases and hence the image quality also decreases. So these are the 2 examples which illustrates spatial and intensity resolution. Next is the next thing, the last thing under this sampling and quantization topic is image interpolation. Interpolation is a tool which is used to resize the image, like zooming or shrinking of the image or rotating the image or geometrical corrections. So interpolation is used to modify the image or resizing of image such as zooming, shrinking, as well geometric corrections and all. So interpolation is also called as resizing or resampling of images. Resampling of images. So here, in order to resize the image, we have to resample it. That means the number of samples which we have considered in the original image should be varied. For example, if at all I consider an original image of 500 cross 500 pixels. Now this is the original image. Now I have to zoom this image, or like I want to enlarge this image 1.5 times, and then I should convert it into 750 cross 750 pixels. So how to enlarge this original image and convert it into new size? So this can be done by creating a grid of 750 imaginary grid, by creating an imaginary grid of 750 cross 750 pixels, and then this grid will be having the same spatial locations as that of the original image, okay, and this image should be shrinked in order to fit into the original image, so that this original image is enlarged or modified to the new pixel values. So now when this image is enlarged into this particular size, some of the new samples gets added, new pixels gets added to this particular image, right. So, and these new pixels should be assigned with new intensity values. So, for that we go for nearest neighbor interpolation. So, this is the method which we use so whenever you modify the size of the original image and enlarge this into 750 cross 750 pixel, then some new pixels gets added into this, and we have to assign new intensity values to these new pixels. How can we do that? That can be done with this method, that is nearest neighbor interpolation. So in this there are again two types, bilinear interpolation and bicubic interpolation. See, in this bilinear interpolation, the new pixel is assigned with new intensity value by considering the 4 neighbors around that particular pixel, by considering the intensity levels of those 4 neighbors which are around this particular pixel, which we call as bilinear interpolation. And here in this we do that with the help of 4 coordinates, with the help of this equation. So using this bilinear interpolation equation, we assign new intensity value to the new pixel by considering its 4 nearest neighbors. Next, in bicubic interpolation, here to assign new intensity value to the new pixel, here in this we consider 16 nearest neighbors of that particular pixel. By considering the intensity value of 16 nearest neighbors, we assign a new intensity value to this new pixel using bicubic interpolation. So here in this method we use the formula So using this formula, we assign new intensity value to the new pixel by using bicubic interpolation. So this is all about the basic concepts of sampling and quantization. Next, to illustrate image interpolation with an example, consider this figure. Now look at this first figure. So this figure 1, this image is having 72 dpi. So this is a degraded image and this is a very poor quality image. So by using nearest neighbor interpolation, this image can be converted into its original form. So it is resized and it is converted into original form. So now the last image is the high quality image, that is the original image having 1250 dpi value.